Welcome to The Explainer. Today, we're going to tear down how an instant messaging app like WhatsApp actually works. And let me tell you, it's probably not how you think. The real secret to making these apps feel so fast and so reliable has almost nothing to do with building a better database and everything to do with understanding how we, as humans, perceive time and correctness.
Right, let's just get this out of the way first. It is so easy, so tempting to look at a chat app and think, oh, it's just a database with a pretty chat window on top. But I'm telling you, that mental model is a trap. If you start there, you're going to end up building something that's slow, super fragile, and frankly, a nightmare to use.
So if that's the wrong way to think about it, what's the right way? Well, the answer is you have to design for human perception first. And once you do that, it changes absolutely everything about the architecture.
Okay, so if it's not a database, then what is it? You have to think of it as a system that is completely obsessed with one thing: latency. It's all about how long it takes for you, the user, to feel like your message has sent. The whole system is built to make the experience feel instantaneous, even if behind the scenes a bunch of stuff is still catching up.
And here's the crucial trade-off. Prioritizing that perfect by-the-book database consistency, where every single server has the exact same data at the exact same millisecond. That is a recipe for disaster here. Why? Because that kind of perfection requires coordination between servers, and coordination is the enemy of speed. In a chat app, even a 100-millisecond delay feels like an eternity. It's a trade-off you just cannot make.
All right, let's get into the nuts and bolts. How do you actually build for human perception? Well, it really boils down to two huge architectural ideas, two main pillars that completely change how the system works.
Pillar number one is the communication channel itself. You see, most of the web works on a request-response model. Your browser asks for something, the server gives it. But chat uses something different, a WebSocket. Think of it like a dedicated open hotline between your phone and the server. It's always on. This means the server can literally push a new message to you the instant it gets it. It's a total game changer compared to your app having to constantly ask the server, hey, got anything new for me yet? How about now?
And this is exactly why they are the perfect tool for the job. Chat is all about tons of small, frequent messages that need to feel instant. And most importantly, the conversation is often server-initiated, right? The server needs to push a message to the recipient. Trying to do that with the old request-response model would just be clunky, inefficient, and super slow.
Now for the second pillar, and this one is a really radical design choice. Instead of trying to guarantee that every single message across the entire platform is in one perfect universal order, which would require this massive, slow coordination effort, the system only guarantees order inside a single conversation. It's a brilliant move, because by letting go of a guarantee that, let's be honest, nobody actually needs, the system gets a huge boost in performance.
And this is such a profound insight for anyone designing systems. We perceive correctness locally. As long as the messages in your chat with your friend are in the right order, that's all that matters. You have no idea, and you have no reason to care if your message was technically sent before or after a message in some completely separate conversation halfway across the world. The system is optimized for what you actually perceive, not for some theoretical, perfect ideal.
Okay, so how does the system tell you that everything's working correctly? It does it with something called acknowledgements, or ACKs. And these aren't just a simple, yep, got it. They are very specific, staged updates that basically tell you the story of your message's journey.
These three stages directly answer the three questions that are always in the back of your mind. First, did my message even go through? That's the sent ACK. Then, okay, did it actually get to their phone? That's delivered. And finally, the big one, did they see it yet? And that's read. See? Correctness isn't just a yes or no, it's a progression.
So with those principles in our back pocket, let's actually trace the complete journey of a single message from the moment you hit that send button.
Okay, so you type your message and hit send. It zips across that open WebSocket to the server. The server immediately gives it a sequence number, but remember, only for that specific conversation. Then it saves the message to storage and right away sends you back that sent ACK. Only after it's been safely stored does the server start the process of fanning out the message to everyone in the chat.
And this right here is a non-negotiable golden rule of the system. Hard invariant. You must save the message before you try to send it to anyone else. Think about it. If you did it the other way around, and the server crashed after sending but before saving, that message would be gone. Poof. Forever. This design guarantees at least once delivery,
which means you'll never lose a message, even if a rare failure causes a duplicate to be sent. It's a trade-off that puts reliability first.
Okay, so this all sounds great on a whiteboard, but this is where the rubber meets the road. How does this architecture actually hold up when things inevitably, and they always do, go wrong in the real world?
This is probably the most common failure you can think of, right? You walk into an elevator, you drive through a tunnel, your network connection just drops. What happens to all the messages people are trying to send you in that moment?
Well, because the system isn't trying to force real-time delivery at all costs, it handles this so gracefully. The server doesn't panic, it just waits. It holds onto your messages in a queue. The very moment you reconnect, it sends that whole batch down to your phone. And thanks to those conversation-scoped sequence numbers we talked about, your phone puts them all back in the right order. No data lost, no mess.
The system is also really smart about what's important. It separates all the traffic into two different lanes. You have the data plane for the actual messages. This stuff is sacred. It cannot be delayed. But then there's the control plane for things like your online status, those is-typing indicators, or read receipts. These are treated as best effort signals. This brilliant separation prevents a storm of typing indicators from ever getting in the way of an actual message.
And this thinking extends all the way up to server failures. The architecture is sharded, which is a fancy way of saying it's broken up into tons of independent mini-systems, usually by conversation. So if one server goes down, it only affects the conversations that live on it. The rest of the app just keeps working fine. This principle of containing the blast radius is absolutely key to building resilient, massive systems and preventing a small fire from becoming a total system meltdown.
So, all of this really brings us to the most important point of all, having the correct mental model from the get-go. Because if you start with the wrong assumptions, I guarantee you will build the wrong system.
And this is a classic trap that even really senior, really smart engineers can fall into. They reach for the most robust, theoretically correct solution. They say, let's guarantee perfect global ordering, and let's guarantee exactly once delivery, which is notoriously difficult and expensive to achieve. It sounds like the right thing to do, but it's a trap.
Because in the real world, chasing that academic perfection adds a ton of coordination that just bloats the latency. It creates all these dependencies between systems that can lead to cascading failures. And what's the end result? You get a system that's slower, more brittle, and delivers a much, much worse experience for the user. So here it is. This is the single most important thing to take away from all of this. In a system like this, correctness is a UX contract, not a database contract. It's not about being theoretically perfect. It's about what the user feels. Does it feel fast? Does it feel reliable? That is the only contract that actually matters.
And so I'll leave you with this question to chew on. It forces us to redefine what correct even means when we're building systems for people, not for machines. If the user feels like the system is instant and reliable, and all the data eventually lines up and becomes consistent, isn't that, by definition, correct? Something to think about.